Oh, this is Zhaoyi Ye, and the ID is A59015863. And this is the homework 3 for MAE 280A. And in this homework, we are required to reduce the midterm and illustrate the solutions we generated. So we have here's the video and the solution I have done. So from the first exercise, which is the linear maps and matrix representation. So in this one, we first have the linear operator A from the R2 by 2 mapping to a R2 by 2. So for the matrix of E, which contains the bases E1 to E4, and we can generate the AE1 is from 100100 to 0100, which is equals to E2. And AE2 is similarly equals to E4, and AE3 is equal to E1, and AE4 equals to E3. So the matrix representation of A with respect to the basis of E is this one, which here is E1, E2, this row is E2, E3, and E4. For this column, it represented the AE1, which is equals to E2, so here is 1 and others are 0. And this is E2, which equal AE2, which is equals to E4, and AE3 equals to E1 here, and AE4 equals to E3 here. So here, this is the matrix, which A is a 4x4 matrix. So as similarly as the exercise 1A, we have exercise 1B, which the basis is different, but the ideas are the same. So we first find the linear combination of the basis to the AB, and then we can add them into this 4x4 matrix. So AB1 is 1101, which transforms from this one by A, and it's a linear combination of minus B2, minus B3, and minus B4. And AB2 is equals to B3, and AB3 equals to B2. AB4 is equals to B1 plus B3. So here still as the exercise 1A, here this is B1, B2, B3, and B4. For each column, we have AB1, AB2, AB3, AB4. AB1 equals to minus B2, minus B3, and minus B4. So here are 3 minus 1. And second one is equal to B3. So it got a 1 at the third row. This got a 1 at second row. And last is the B1 plus B3. So it got a 1 at both first row and the third row. So this is the matrix representation of the B with respect of A. And then we come to the second exercise, which is the linear maps and their subspaces. So here is the map generated by the question. This is RP. By mapping C, we have Rn, and by mapping A, we have Rm, and by mapping M, we have Rq here. So this is the mapping RAC, and this is mapping RBA. And so first one, I'm asked about the null space of BA is equals to null space of A. To think about this question, we can think this equation by both ways. So we can generate the vectors the null space of A is the subspace of null space of BA, and the null space of BA is the subspace of null space of A, which we can finally to prove they are equal. So first we prove that the null space of BA is a subspace of null space of BA. So we suppose that X belongs to Rn. So when X belongs to null space of N, we have AX is equals to theta M, which belongs to Rn. And by applying BAX, which here, and we have theta M here, we have the theta Q, which is which shows that X belongs to null space of BA. So which we can prove that null space A is the subspace of null space of BA. So inversely, we can think about we can generate a similar thing by first we assume there is a vector y belongs to RQ, which y is belongs to null space of BA. So we can have BAY is equals to theta Q, which here is in RQ. And we also can suppose that there is a y hat belongs to RQ, which by height is equal to theta Q, as y hat is the null space of B. And since B is injective, that everything in the matrix in the space which will be mapped have a respective element in the space which have been mapped. So there is only the zero vectors in the null space will be linear mapped to the zero vectors in the mapped null space, which simply as theta m by mapping B is equals to theta Q. And so according to this one, we learned that the BY hat is definitely equals to BAY, which we can prove that Y is belongs to the null space of A. So we can say that since BY is also a null space of BA here, we suppose that's the beginning. So we have that null space of BA is the subspace of null space of A. So by having both these equations, we can conclude that null space BA is equals to null space of A. And similarly, we have the question 2, which has a similar idea. We are required to show that the range of AC is equals to range of A. So first one, we suppose that there is a vector belongs to range of AC, which we can say that the AC so there also exists respects vector Rx, which is belongs to Rp from here, so that YACX is equals to Y is equals to ACX, and which we can also equals to YAX hat, so that we can get CX is X hat. So since that Y is equals to AX hat, we can have that Y is also in the range A. So we can conclude that the range of AC is subspace of range of A. So, and then inversely, we can think about, suppose there is a vector Z that in the range of A. So there is a U in the range N, which is here, and it could be mapped by A, and it could be mapped by A, and we have that Z is equals to AU, and also since C is surjective, so everything in A have a, so that it means that everything in A everything in Rp in Rn has a respective element in the space of Rp. So we can conclude that there must exist an element vector at V belongs to Rp. It could be at least one or more, so that the Cv is equals to U. So by applying U equals to Cv here, we can find Z is equals to AU also equals to ACV. So we can conclude that Z is also a vector which belongs to the subspace range of AC, and so we can conclude since Z is also in the range of ARA, so we can conclude that the range of AC contains the range of A. So we have the by combining both these two equations, we have that range of A is equal to range of range of AC. And then we come to the exercise 3, which is the Lipschitz continuity. So in the first one, first I will illustrate the extra credit part. So which is f and q are both Lipschitz continuous in x and y. So we can generate a two Lipschitz continuous inequalities, which ky is the Lipschitz functions for f1 and the k2 is the Lipschitz functions for f2. For g, and so which g circle f x1 minus g circle f. To prove that it is Lipschitz continuous, we have to generate the inequalities similar like this one. So first we write the left hand side, which is g circle f x1 minus g circle f x2, which according to the question, we will take the g of x fx1 and g of fx2. We suppose fx1 equals to y1 and fx2 equals to y2, which from here we can apply these inequalities by replacing this one by y, and we have this one, which is k2, which this is a less or equal, which shows the inequalities here. And by replacing fx1 and fx2 here, and we can, this one is equals to this one, and so the whole equation, the whole function is this one, which is the k2 multiplied by k1 and multiplied by the absolute norm of the x1 minus x2, which k1, k2 is the Lipschitz function of the g circle f. So g circle f is the Lipschitz continuous. And so after the extra credit, so in the normal conditions, we can suppose that there are two functions. The first one is simple as fx equals to x, and second one is the which is not continuous function, which like this. We can generate it to suppose that gx is equals to 0 when x is smaller than 0, and gx equals to 1 when x is larger or equal to than 0. And so from this one, we have g circle fx is equal to g of fx, which is equal to gx. And gx, as we have showed here, it is not continuous, so it is not a Lipschitz continuous function, which is the counterexample of first one. So the result is that g circle f is not Lipschitz continuous if f and g are not, if either f or g is not Lipschitz continuous. And then we come to the second question 2, which first we can generate it that these two questions with the suppose that there are kf and kg are Lipschitz functions to fg and gx, to fx and gx respectively. And so similarly as this one, we combine them together and doing the try to do the equalities. So by expand this one, we have fx1 plus gx1 minus fx2 minus gx2 norm, which is less or equal to fx1 minus fx2 plus norm and plus the norm of gx1 minus gx2. This is hold for because of the norm of the sum is less or equal to the sum of the norm. So, and this one, by applying back to these two equations, we can find that it is less or equal to kf plus kg, and in the norm of x1 minus x2, which shows that it is Lipschitz continuous. And the answer is the f plus g is Lipschitz continuous, and kf plus kg is a Lipschitz function. And then we come to the exercise 4. I will add the conclusion here. And this is exercise 4, which first one found the matrix, we are required to find the matrix AT for the transfer function respective to this transition function. So since the phi t, this is the transition function of the system. Since the phi t0 is equal to I, and d over dt, the derivative of this transfer function is equal to at phi t0. So by giving t equals to t0, applying to this function, we have that when t is equal to 0, the derivative of this transfer, the phi t0 is equals to at. So from the for state transition matrix given, we can have we can use this we can calculate this derivative, which is the result is here from by taking this derivative, which is the that of the 1 over that multiplies the minus c minus a b d, which b d here, and this is minus c and minus a, and this is the result. So therefore, since here we took t equals to 0, so at0 is equals to t. So here is t0, and t0 square minus t0 square is 0. So the exponential part here is equals to 1. So at0 is equal to 0, t0, 0, t0 for all the t0s. And which we got the solution. And the second one is to find the different, to show that there is a solution. And so to prove that it is a solution given, we have to prove it satisfies the two conditions. First one is the initial condition and the differential equation. So for initial condition, we apply t0 to t to the equation x. And here is phi 1 t0 t0, which is I, and phi 2 t0 t0 the inverse, which is also I. Then in the middle, there is x0. So x t0 is equal to x0, which satisfies the initial condition. So for the differential equation part, we first differentiate the x by, and this one is generated by the product rule, which first one is take the derivative of phi 1, and this one takes the derivative of phi 2 inverse. And phi 1 the derivative of phi 1 is equal to a1t phi t0. And to calculate the derivative of phi 2 inverse, we first think that phi 2 multiplied by phi 2 inverse is equals to I, which implies that which derivative of both sides we have this one, and also generated by product rule here. And so by abstract to remain the phi 2 minus derivative here, and we move all these stuffs to the right hand side of the equation, we can generate that so the derivative phi 2 inverse is equals to the phi 2 inverse derivative of, multiplied by phi 2 derivative of phi 2 and multiplied by phi 2 inverse. So since we can similarly get the derivative of phi 2 here, we have phi 2 inverse multiplied by a2t multiplied by phi 2 and multiplied by phi 2 inverse. Since phi 2 inverse multiplied by phi 2, which is here, equals to I. So the derivative of phi 2 inverse is equals to the minus the phi 2 inverse multiplied by a2t. So applying this one back to here and applying this one to here, we can generate this equation, and we can say that the phi 1 multiplied by x0 multiplied by phi 2 inverse is x. So this one is x and this one is x, which the derivative of x equal to a1 tx and minus x multiplied by a2t. So which is the matrix differential equation given, so which satisfies the differential equation. So the solution satisfies both initial conditions and differential equation, which means that the solution is the solution is the is the one that the question gave us. And that's all for my homework 3. Thanks.